In this section, we're going to focus more on some of the terms, some of the different categories, methods, so on and so forth when it comes to machine learning. Again, don't be too worried about this section. If it's too theoretical for you, that's okay. The rest of the course will be focused on actual application, and I'm going to be going into a lot of examples, and we're going to be writing a lot of code, a lot of R code, solving actual problems and training actual models using actual data. So this section is intended more as a brief introduction, just so you can get familiar with some of the concepts, but it's not crucial. And I'm going to be going over a lot of important concepts in each of the future sections as well, concepts that relate directly with machine learning itself. This section is more just like general information. So there are three main machine learning categories, or we can say that machine learning, the space of machine learning has traditionally been divided into three broad categories. And these are supervised learning, unsupervised learning, and reinforcement learning. I'm going to be explaining each of these in a little bit more detail in the following slides, but keep in mind that reinforcement learning is something that we're not really going to be doing in this course, and it's not something that a lot of machine learning courses actually go into. Reinforcement learning is kind of its own thing, and it has its own unique set of problems that it aims to solve, and it's not really that applicable to business problems. Supervised learning is the most common method because most problems require supervised learning, and you'll see why when we get into the definition of supervised learning. And then there's a little bit of unsupervised learning, but reinforcement learning is pretty much left out in a lot of these type of courses. Now, supervised learning is the number one most crucial category that you should know about, and it's the category that a lot of the machine learning algorithms that we're going to be using fall into. And the main difference between supervised learning and, let's say, unsupervised learning is the fact that the training data is labeled. Okay, so for each instance in the training data, the right answers or results, also called labels, are given. So if we go back to the example from part 1 with the digits, the data that you're feeding into the algorithm, into the program, needs to have the correct labeled digit for each image. Or for loans, you need to supply data to the algorithm in which each instance has a column that specifies whether or not that loan defaulted or not. So the algorithm needs to have data that connects the input to the output, where the output is actually labeled and actually given. And it uses this input-output connections or input-output examples to develop a connection or a relationship between the input and output. There are generally two categories of supervised learning, one called regression and one called classification. So regression is aimed at predicting outcomes that can have a continuous range. So for example, a number. So regression problems are problems in which the outcome variable is numeric or continuous. And classification problems are supervised learning problems where the outcome variable is discrete or categorical, right? There are discrete, specific, distinct classes, such as, yes or no, in the case of a loan defaulting, or 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? In terms of, digit classification, it could only be one of those 10 digits. It's not a continuous variable. It's not a numeric output, okay? These are the two main types of supervised learning algorithms, and most of what we're going to be covering in this course falls into either regression or classification, and actually most of them can be used to solve both regression and classification. So if a problem is designed to solve a classification problem, you can actually ensemble together multiple versions of that model and create a regression trainer as well. So we're going to go into all of that in the future, but the main point is that supervised learning's main focus is on predicting the future. So predicting the outcome of future instances or future cases. And, in order to do that, we train on historic data, on previous instances. some of the most important supervised learning algorithms, and the ones that we're actually going to be covering in this course, are linear regression. Okay, first of all, linear regression is the father of supervised learning, and it's basically the original supervised learning algorithm. Actually, that might not historically be correct, but we can say that it's the one that's most often first taught because it's the simplest to, it's the easiest one to use to explain or to showcase how machine learning works. But at the same time, it might be one of the most misunderstood or misinterpreted algorithms as well, because it comes originally from statistics, from statistical learning, and there's actually a lot of theory behind it. And it's not as easy to interpret its results as many data scientists might believe. You have to use it with caution. In most cases, you won't have a problem, but just know that there is a lot of statistical background to this algorithm. So linear regression is a regression. We said that there's a regression and classification algorithms or tasks in supervised learning. Linear regression is, as you can see, it's in its name. It's used to predict numeric output, continuous output. Whereas logistic regression, even though the word regression is in the name, it's actually a classification algorithm. So it's used to classify or predict discrete outcomes. Support vector machines are also very common, very popular. And again, I'm not going to go into too much of the theory or the history behind these algorithms. There was a time in the past where you would need to know more about the differences and the nuances between these algorithms. Nowadays, you can pretty much use them interchangeably. Some might say that's bad advice, but you'll pick up the nuances as you use them. But in each respective section for each of these algorithms, I will go into the theory behind it, so you will understand how they work. But this is, again, more of an introduction here in this section. So support vector machines, or SVMs, decision trees are also very common and very powerful. And when you combine a bunch of decision trees into an ensemble, you get another algorithm called random forests, which is nowadays probably one of the most common machine learning algorithms. And you might have heard about Kaggle, Google's machine learning competition website. And there was a time when random forests were really dominating that platform. And so that's before deep learning and stuff got so popular. And then we have k-nearest means and neural networks. So neural networks are also supervised learning algorithms. They require labeled data sets. So, if you want to train a very large neural network for, let's say, image detection to use for autonomous cars, you're going to need to supply the neural network with tens of thousands, maybe hundreds of thousands, or even millions of images that have been previously labeled. And that's not an easy task. That's kind of why a lot of big tech companies are dominating the deep learning or neural network arena currently, because it does take a lot of resources to not only train the model computationally, but to also prepare the data. Imagine having to classify 1 million images. You can't do that on your own. There are systems in place like Amazon Mechanic Turk and that kind of stuff where you can outsource that work to other people, but still, it takes quite a bit of resources, time and money. So that's supervised learning. Let's go into a little bit into the differences between regression and classification. So regression is used to predict a target numeric value given a set of features called predictors. So the set of features or the predictors, those are the input variables. Okay. So let's say we want to predict the price of a car, okay, given some set of features or predictors or input variables, which can be, for example, the mileage of that car, how old it is, its brand, its model, how much gas it consumes, how many people have owned it in the past, so on and so forth. And so each one of these would be a feature, a predictor, a variable, an input into the algorithm. And the output that we're trying to predict is the price of the car. Now, the price of the car can be any of, a whole range. It's a continuous variable. It can be any number, hypothetically, right? It's not a discrete output. It could be 5,000. It could be 5,010. It could be 5,320. It could be 6,000, right? It could be any of a range of numeric numbers. And so in order to train a model on this, the price of it, we need to use a regression algorithm. So this is supervised learning. Why? Because we need to supply it with historic data with actual prices of cars in order to train it. So we supply it with labeled data, but we're predicting a continuous output, a continuous variable, or a continuous outcome, and that's why it's a regression. So to train the system, you need to give many examples of cars as input, including both their features and their labels. So you need to give it historic data or existing data on cars, on actual cars, with their given mileage, their age, their brand, all of the features we talked about, and the actual price of those cars. That's what we mean by labeled instances. So that data is labeled because the output variable, which is the price of the car, is given to the algorithm. So the algorithm has actual data and knows the price of those cars, of whose data has been given to the algorithm. And so it uses that to train itself. So that's why it's supervised learning. And because the outcome variable is continuous, it's called regression. Okay. Classification, on the other hand, predicts a class or category. So let's say we want to predict whether a new email is spam or not. To train the system, you need to give many examples of emails along with their class. So whether or not that email is spam or not. So, let's say you go into your inbox, you pull out all your emails, you go through them one by one and label which ones are spam and which ones are not. And that's your training data. That's labeled. It's labeled, and therefore it's supervised learning. What you're trying to predict, the outcome variable, is basically yes or no, true or false. Is it spam or not? So there's two classes, two categories you're trying to predict. There's no continuous variable, right? And therefore it's a classification problem, and you need a classification algorithm to solve it. Now that's for supervised learning. Again, most of that, we're going to go into in more detail in the following sections. Let's now talk briefly about unsupervised learning. So unsupervised learning is trained on data that is unlabeled. So you might say, why would you give it unlabeled data? Why don't you label it? Because sometimes you don't know what to label data. So let's say that you have, for example, Netflix, for example, has data on what types of movies you've watched, how long you've, been watching a particular show, or, how many times you viewed a certain movie or something like that, right? They have all this data and they want to recommend something for you to watch. They don't know what you want to watch. They can't predict it. They can't know for sure. Nobody can look at what you're watching and label that data and be like, okay, this guy wants to watch this, right? So there's no way to actually label training data in that case. So if you want to build a model that can take in that data that has no labels, and from that data come up with some sort of recommendation system where it can actually recommend for you a movie that you might most probably be interested in watching, that's unsupervised learning, because the input data has no labels, okay? So in unsupervised learning, instances in the training data are not presented with right answers or outcomes. Therefore, the system tries to learn without a teacher, if you will. Okay, so some typical unsupervised learning tasks include clustering or cluster analysis. That's where you have a bunch of data and you want to train a model on it that can cluster or group certain instances together based on that data. So let's say you're a company and you're selling certain products and you have a lot of information on your consumers or your customers, and you want to create categories of different types of consumer or customer based on that data. So you don't know what type they belong in because you haven't come up with the categories or types yet. So you can't label your data set, your training data set. So it's unlabeled. So you use an unsupervised learning algorithm to train on that data and present to you with some possibilities for different categories within your customer's database, right? Like it might find that there are certain types of customers that just tend to have similar values for certain variables. Another type have different variables. Then analyze these two groups and come up with different marketing strategies for them, for example. So that's clustering. We're going to go into clustering. There's going to be a section on clustering. And I think that might be the only unsupervised learning algorithm that we implement in this course. Again, like I said, most machine learning courses, they focus on supervised learning because that's how you solve most business problems. But I will be presenting to you an unsupervised learning problem and solution as well in one of the sections. Another problem or another task that's solved using unsupervised learning is dimensionality reduction. And that's where you have a data set that has way too many features or way too many variables. And you want to reduce this data set down to, just a few crucial variables without losing any crucial information or any crucial data. And so that's a pretty difficult task because as the number of variables increases, the problem gets exponentially harder to solve. So, we use unsupervised learning, machine learning, to solve this problem. I might go into that if we have time later in the course, but that's a little bit more of an extreme example. So, I might not bother going into it. Anomaly detection is another very good example of unsupervised learning. That's where you want to train a model that can detect anomalies in certain data sets. And, the whole concept of something being an anomaly is that you don't know that it's going to happen. So it's very hard to label data or to come up with a training data set for anomaly detection. Or label data set. So, unsupervised learning is also used to solve those kind of problems.